Today we're going to talk about the principle of general covariance, and so it's a new principle that we are going to introduce, because up to this stage we worked with the principle of equivalence, and well, we discussed what it is based on, and the point was that we could use the principle of equivalence to write equations which were supposed to be generally valid in gravity, because we would write them first in a freely falling frame, right? The frame that falls from the Tower of Pisa. You write down what the equations are. They're given by the laws of special relativity, right? For example, the particle motion or Lorentz force, right? Valid in special relativity. And then you do a coordinate transformation, right? So you go from coordinate x to coordinate x prime, right? And the original coordinate was, in fact, an inertial coordinate system. So this was actually xi, right? This xi alpha coordinate. And so then you do a general coordinate transformation, and you end up with this equation of free fall, for example, right? That you can write down, which looks like it would be valid in any system of coordinates, not just the freely falling one. So that is a very cumbersome procedure, very complicated to do this coordinate transformation. So we're going to work instead with a different principle, which is the principle of general covariance, which is equivalent to what we've used so far. And so the idea of this principle of general covariance is then you first write down an equation which is valid in an inertial frame, right? So that would be the kind of equations that we wrote down at the beginning of this class when we talked about special relativity. Particle motion, perfect fluid, equations of motion, and so forth, right? And then the next step is to make sure that these equations are generally covariant. That is, they are form invariant and they're valid in any coordinate system. So write them as invariant equations, right? Write them as equations that, so invariant equations means that they have the same form in any coordinate system, right? They have the same shape, right? And so that requires that we do a little bit more of tensor analysis, and we understand how exactly you write down an equation that is actually form invariant. Because in order to have an equation that is form invariant, it has to be written in terms of tensors. And so we have to understand what type of tensors you can have and what constructions you can make out of those tensors. You can take linear combinations, direct products, differentiation, all sorts of things you can do. And so we have to learn the mathematics of that, which is something that normally we don't get exposed to too much, right? It's still basic multivariate calculus, but nevertheless we have to learn the rules on how to combine tensors together so we know how to construct something that is invariant, right? And so before we plunge into that and discuss this kind of properties of tensors and vectors in general relativity, let me talk a little bit about the principle of special relativity. The principle of special relativity is what we used in the first 3 lectures or so, right? We did use an invariance principle to write down equations that were invariant, specifically Lorentz invariant, right? We learned to use symmetry principles to extract things that would have the same form in any coordinate system, and that was basically the principle of special relativity, right? And so here we have something that is similar, which is the principle of general relativity, right? And the principle of general relativity is an extension of the first one, where you try to write equations which are valid in any coordinate system. And what is interesting is that when you go from this part of it to the second part, right, both have to do with coordinate transformation, but in the first case, it's just a coordinate transformation, which is x independent. In the second case, the coordinate transformation, the symmetry operation, depends on the location, right? And that, of course, is similar to what happens in electrodynamics, because in electrodynamics, at first you have, when you write down the Schrödinger equation or the Dirac equation, you have an invariance under phase transformations. You can rotate the phase of the wave function, right? And when you promote that to a local invariance where you can change the phase locally at each x, that requires in QED, right? In QED, that requires that you introduce an electromagnetic field, otherwise you don't have local invariance, right? And that is the reason why when you couple a particle to an electromagnetic field, you have to do the replacement in which the derivative is replaced by d mu minus IE over h bar c times a mu. That is, you have to introduce a gauge field so that you have a local invariance under phase transformations. And that carries over also in non-abelian gauge theories like QCD and so forth. You have to have a certain number of gauge fields that makes the local invariance possible. And gravity is a gauge theory. Gravity is in fact a gauge theory. There is a deep analogy with QED, right? And so it happens that when you go from the invariance of special relativity to the invariance of general relativity, you have to introduce certain fields, which are like the photon field. And so those fields are, in fact, the g mu nu of x and the gamma lambda mu nu of x, right, which are related. Second one is just derivatives of the first one. So the g mu nu and the gamma lambda mu nu are the analog of the electromagnetic field, and they are gauge fields. They're gauge fields. They ensure that you actually have this local invariance, right? In special relativity, you have a global invariance under Lorentz transformations, which are done by the same amount everywhere, right? Whereas in special relativity, the transformation is done locally. It's a function of x, right? And that's tremendous difference, right? And so that forces you to introduce gauge fields, right? And so we are going to use this principle of general covariance to construct equations which are invariant under this new symmetry, which is general coordinate transformations, and that is similar to what we do in QED, where also we want to have everything to be gauge invariant, right? Now, when we take quantum field theory class, we understand at some point the importance of gauge invariance and preserving gauge invariance through, for example, the normalization process. Because if the theory is not gauge invariant, like QED or quantum dynamics, then the particle acquires a mass. The photon becomes massive, and that's, of course, a catastrophe because the photon is supposed to stay massless, right? So there's certain identities called word identities which follow from the fact that you have gauge invariance. So in the case of gravity, it's the same story, right? This fundamental invariance plays a role at the classical and at the quantum level. You need to preserve it always so to make sure that the graviton does not acquire a mass of the order of the Planck mass or some gigantic mass. This invariance plays a role all the way to anything that we have done in the past and that we do today as far as gravity. It's very important to preserve this local invariance. In fact, this local invariance is the reason why in general relativity you have local conservation of energy and momentum, right? The fundamental invariance of QED, which is a local conservation of charge, appears in the theory of general relativity as a local conservation of energy and momentum. So if energy and momentum are locally not conserved, then you've broken general covariance. So that can never happen, and that is why it's always locally preserved. And that is one of the fundamental principles that underlies GR, is this local invariance, right? There is, again, if you do quantum field theory, at some point you learn about Noether's theorem. Emmy Noether was the lady that wrote down a theorem back in the early 20s, which said every time you have a symmetry, you have a conservation law. And so that's the general principle of any field theory, and it applies, of course, to gravity too and QED. In QED, the local symmetry is phase invariance. So you rotate by a phase. There is the symmetry. As a consequence of that symmetry, you have a conserved current, and that is the electromagnetic current, which ensures that the photon stays massless. In general relativity, you also have a local symmetry, which is general coordinate invariance, right? And that symmetry ensures that then you have exact conservation laws, not approximate one, exact conservation of local energy and momentum at each point in space-time. And in fact, the appropriate statement is that if you have something like matter or perfect fluid, then you have that the covariant divergence of the energy momentum tensor is 0 at every point in space and time. So we have to learn a little bit. Now we are going to do quite a bit of mathematics now, and you have to bear with me because that's how it happened historically, right? There's this step in trying to understand how you actually construct something that is generally covariant. Because if you try something simple, right, you might say, well, you know, let spare me the detail, you know, of all this tensor stuff, and let's just get to the equations. And yeah, we could do that. But there was a struggle because, remember, what we have learned so far, right? We have understood that, first of all, there is this object, g mu nu of x, which seems to play an important role, right? And related to it is this gamma lambda mu nu of x, which also seems to play an important role because it appears directly in the equation of free fall, which is one of the two fundamental equations of general relativity, right? What we have learned so far is that in the non-relativistic limit, we know that g naught naught of x is equal to minus 1 plus 2 phi of x. We have learned that at least the g naught naught is related to the gravitational potential, right? And so if we want to write down some sort of equations for the gravitational field, we have to write an equation for the g mu nu. So you can imagine, and this is of course what happened historically, but we can repeat the same argument in this class, that you would imagine that the first thing you would do is, well, I do know what the equation for phi is, right? Because I know that when I just look at static gravitational field, that I have Poisson's equation, right? 4 pi g times rho. So I know that I can relate the gravitational field to the distribution of mass, density rho, right? And well, this equation is not Lorentz invariant, right? So now I want to write down something that is going to be valid in some more general coordinate systems. And so, well, what I'm going to do is I'm going to first take a thing, right, that is kind of relativistic invariance, which is some sort of box, right? And I have understood at this point that there is a metric which is going to play an important role, and so I'm going to write box g mu nu. And well, I know that the source for the gravitational field is supposed to be something that contains the rho as the naught naught component, and so the Newton's constant should appear somewhere, and so the candidate equation is something like this, right? So we have, right, if we're kind of bold and adventurous at this point, we might say that we are looking for an equation which is a generalization of Poisson's equation, which involves some relativistic operator, like you have in a Klein-Gordon equation, for example. The box, the Lambertian, right, acting on not 1 but 10 fields, because we appreciate by now that you probably have 10 of those. And what you have to put on the other side of this equation is an object that A describes the distribution of energy and momentum, and B has 2 indices, right? There's 10 components, and so that's the T mu nu, that's a prime candidate, right? And so this is very much like the equation for electromagnetism, right? Where you have box A mu is equal to J mu, where J mu is the electromagnetic current. So you could try something like that, and of course you get nowhere. This doesn't work. It doesn't work because basically the box of g mu nu is 0 identically, right? And so this equation is not very useful, right? So you have to think quite a bit more, right? The equations eventually turn out to be written in terms of the affine connection. Well, maybe not even that, because it's in terms of derivatives of the affine connection, and those are related to the Riemann tensor. So it's actually the Riemann tensor that eventually appears in the equations of motion for the gravitational field. And those equations are nonlinear. This is a linear equation, right? But it is characteristic of gravity that you get a highly nonlinear equation. And they're much more complicated, even though they're actually quite simple and elegant in the end, once you can see through the mathematics, right? So this does not work, right? So that is a justification for the fact that we really have to take a step back and understand how we deal with this general coordinate system. How can we actually write down something that is invariant under general coordinate transformation, and which eventually is going to be a candidate for the field equations. Now, the remarkable thing about this whole procedure is that once you have gone through tensor algebra and tensor calculus, once you understood how you take derivatives of tensors and construct things that are invariant, you end up with a set of field equations which are unique. There's only one. There's no other possibility. And that is kind of amazing, right? It's a little bit like Maxwell's equation. They're unique too. There's only one set of equations describing a massless photon, and that's massless. That's Maxwell's equation. So here the same thing happens, right? And so that is a very important result, because you might think that when you go through all this mathematics, then at some point you get a set of equations that has 137 free parameters in it, right? And now you have to fix this 137 parameters by experiments, yeah, right? And that's not the case. There's only one parameter, and you know that already because it's G. It's Newton's constant. So you get a set of field equations that just depend on G only. Well, not quite. I mean, there's a little tiny thing which you can add, which is the cosmological constant. So there's a new term that actually nobody had thought about before Einstein, before 1916. But apart from that, and it's a very small one, which only plays a role on cosmological scale. So other than that, the field equations are unique. And so in that respect, Einstein was lucky, right? Because it could have been, right, that you had three terms and you had to determine the coefficients of those three terms, or maybe 137, whatever, but here it's just one. So it worked out pretty well. And so as a result, Einstein's theory is unique. The 1916 theory that he wrote down can be written in a very simple way in terms of the Ricci tensor, and it's a unique theory. And it's completely constrained, and it is the only theory you can write down from a modern point of view for a massless spin 2 particle. There's only one. That's Feynman's theorem. If you have a massless spin 2 particle, then the only theory you can write down is Einstein's theory, right? So it's a remarkable result. So as a consequence, we don't want to skip all this stuff, right? We want to understand how it is that it is unique. We want to understand why you can only get Einstein's theory and nothing else, right? And so in order to do that, we have to do tensor algebra and tensor analysis a little bit. And so let's get started by talking about vectors and tensors. Vectors and tensors, right? And so we'll have to introduce some notation and some names. So the first thing we're going to introduce is even before that, we're going to have scalars, right? That is quantities that actually do not change at all when you do a coordinate transformation. So we're going to be interested in coordinate changes where x mu goes into x prime mu, right? So general coordinate transformations, right? And understand how different objects transform under this x goes to x prime. So first of all, you have things that don't change at all, right? So those would be things like pi, right, and the proper time interval, and a few others, right? There's some genuine scalar field, like the Klein-Gordon field is a true scalar. It doesn't change at all when you do a coordinate change. Now, as far as vectors are concerned, there's two different possibilities, and the first possibility is that we have a contravariant vector. Contravariant vector, right? And so that is a vector that has indices upstairs, right? So we're going to call that v mu of x. We will have to be very careful distinguishing objects that have an index upstairs and an index downstairs, because they will transform differently under general coordinate transformation. This distinction is a very small one in special relativity, because in special relativity, having an index upstairs or downstairs just changes the sign of the not component, which is not a big change, right? But in GR, it is a big change, and they're just quite different objects as far as transformation properties and their coordinate changes are concerned. So a contravariant vector transforms as v prime mu, right? And so this is always a function of x and x prime, right? And so this is going to be equal to dx prime mu by dx nu times v nu. Right? So a contravariant vector has an index upstairs, and it transforms via a dx prime by dx. So it is crucial to see that the prime is upstairs and not downstairs, right? And so that should be contrasted with a covariant vector. Covariant vector has an index which is downstairs, and it transforms according to the inverse of this thing, right? So u prime mu is equal to dx nu by dx prime mu times u nu. Right? So you can see that you have dx prime by dx here, and you have dx by dx prime. So, well, those derivatives are clearly quite different in general, right, depending on what the transformation is from x to x prime. I should maybe draw a picture of what the coordinate change is, right? We are not in flat space, right? So in flat space, you can draw a coordinate system which looks like this, right? And right? And so you can draw a Cartesian coordinate system. Now, if you want, you can draw also some sort of spherical or polar or cylindrical, whatever coordinate system. But in flat space, certainly one of the easiest choices to do something like this. But we are not in flat space, which means that our coordinate systems will, well, they will be like coordinates that are put on the surface of the Earth, which is curved, right? So they will look like this to start with, right? Coordinate system will look like this to start with some direction this way and some other direction that way, right? And we're drawing things in 2 dimensions because obviously that's the easiest thing to do. So this would be our coordinate system x, say mu, right? And so a coordinate change means that we set up some other coordinates to describe what is essentially the same manifold, right? Which would be the surface of the Earth, right? And so the new coordinate system would look, for example, like this. Right, so it would be coordinates going this way, and that would be x prime mu. Right? And we are assuming that there is a differentiable function that brings from one to the other, namely that these derivatives all exist and are well behaved and there's no singularity, right? And so that's the derivatives we're calculating here, is the change in coordinates from one set to another, right? And so we have these covariant and contravariant vectors, and the derivative of a field, let me write this in black. So the derivative is a special case. It's a special case because we can take, for example, a scalar field, right, d phi, and take the derivative of that with respect to x mu. And so this is scalar. Right, so a scalar field transforms trivially, right? A scalar field is one such that phi prime is equal to phi. So if we take d phi by dx prime mu, so if we put a prime here, then we can write that derivative with respect to the prime as the derivative of dx nu, dx prime mu, and then times the derivative of phi with respect to x nu. Right? Again, just using rules for differentiation. Right? So that means that this is covariant. Right? So the derivative or the gradient of a scalar field is a naturally covariant object. So now we're going to do a little jump here and go on to a more general tensor that we can have. general tensor is going to be an object that instead of having one or two indices, might possibly have quite a few of them, right? And so let's take one, which we don't want to write down too many indices. So let's say it has 3. And, well, those 3 indices could be upstairs or downstairs. So we're going to take a combination where we have one index upstairs, right? And then one downstairs, and then another one, which is upstairs as well. So a tensor which is like this, which is referred to as a mixed tensor. So this tensor has 2 indices which are upstairs and therefore are contravariant, and has one index which is downstairs. So it is covariant in the index nu, and as a result, the tensor as a whole is a mixed tensor in this form, right? And so how will this transform? Well, the definition of a tensor, right? Definition of a tensor is that it transforms in a simple way, just like the vectors did, right? So this will be equal to dx prime and dx prime and dx prime, right? Where you have the index mu here, the index lambda there, and you have the index nu here, and then you have to introduce new indices like dxk, right, and dx sigma, and dx, let's say rho and sigma, right, and then times the tensor itself, which will have the same number of indices as the original one, so k rho and sigma. Right, so you notice here that that's dx prime by dx, which is appropriate for a contravariant quantity. You have a dx by dx prime for this index here, which is appropriate for this covariant index. And you have a dx prime by dx, again, for a third index, which is appropriate for a contravariant index. So that is the definition of a general tensor. A general tensor will transform under coordinate changes by a product of these dx by d primes, right? So dx by dx prime or dx prime by dx, depending on whether the index is upstairs or downstairs, right? That is a tensor. If it does not transform in this way, then it is not. It is not. Now notice that this is a sort of a linear transformation, right? Because you see that these can be all viewed individually as some sort of a matrix, right? And that matrix is acting on the indices that are associated with the T. Of course, the big difference with the way we normally handle matrices is that all these quantities depend on x, right? So the amount of rotation that is done depends on the point that you're at, right? Because all these derivatives of one coordinate system with respect to another one depend on the point x. Right? So an example of a tensor is the metric itself, right? That is one of the first two index objects that we learned about. And now we start from the definition, right? And the definition is that g mu nu of x, right, was defined, remember, as eta alpha beta, and then d psi alpha by dx mu, and d psi beta by dx nu. Right? That is how it was defined in terms of this change of coordinates from the flat metric, which is described by xi, to the metrics, to the coordinate system that is described by x and mu. Right? And so now we can calculate from that g prime mu nu. Right? Well, from the very definition, g prime mu nu is going to be the same, right? We're just going to use this expression. Is going to be exactly the same where we replace everywhere x by x prime, right? So this is equal to 8 alpha beta times d psi alpha by dx prime mu and d psi beta by dx prime nu, right? That's just from the definition, right? And now what we can do is we can replace each one of the derivatives with respect to x prime as derivative with respect to x times a factor of dx by dx prime, right? So you can write this as eta alpha beta, right? And then d psi alpha by dx, some other x, which we're going to call here dx rho, and then dx rho by dx prime mu, right? And so that is the first piece, right? And then times, same story for the second term, the dxi beta. So dxi beta by dx sigma, and then dx sigma by dx prime nu. Right, so the second term is what we get from that one, right? And now you stare at this expression a little bit, and you recognize that you in fact have two factors which are precisely the factors that you expect for a second-rank tensor when you change coordinate system, right? Because this is precisely equal to dx is equal to d. If you look at these two factors, dx rho by dx prime mu, so sorry, dx sigma dx prime nu upstairs, dx prime nu, and then dx rho times dx rho times dx prime mu times g sigma rho, right? Where we use the fact that this g sigma rho is equal to this combination here with that piece over there, right? So we have that the metric, so this is equal to g prime mu nu, is equal to that. So we have that the metric in fact transforms with two factors, which are dx by dx prime, both of them, and so that's a covariant tensor. Covariant tensor. So it transforms with the indices downstairs. So another object that we introduced was the inverse of G. So we also introduced the inverse of G mu nu, which we called, well, G mu nu with indices upstairs, which we call so G lambda sigma, right? And the relationship we had was that when we took G mu nu and we multiplied by the inverse, we got the identity. So we calculated G, let me write this as G lambda nu, and then take G mu lambda in this way. And so we sum over this index, and so we have standard matrix multiplication, and the two indices that are left over are the first one and the last one. So this is delta mu nu, which is just the Kronecker delta symbol, right? And so this does not depend on x, right? Because this is supposed to be exactly the inverse of that. So when you multiply by the inverse, you get 1. It doesn't depend on x, right? So you can in fact now do the transformation for this one and the transformation that we had from there, and it works out if you have that G prime mu lambda is equal to dx prime mu and dx prime lambda by dx rho and dx sigma times G rho sigma, right? Which says that G, so inverse of G is contravariant. Inverse of G is contravariant. You see, that's what we defined a moment ago to be a contravariant vector or tensor is one that transforms according to dx prime by dx, right? Which is just the opposite of what we have here, because here it transforms through dx by dx prime. So one is covariant and the other one is contravariant. And the Kronecker symbol, so exercise, delta mu nu, or let's write it as the way we did it there, delta mu nu is mixed. Is a mixed tensor, so we're actually justified in writing one index upstairs and one index downstairs, because when you multiply it by dx prime by dx for the upper index and dx by dx prime for the lower index, in fact, those two factors just cancel out and give 1. And so what is the use of all of this? Well, the use of all of this is that we can write down invariant equations. So use of all of this is that one can write invariant equations. And that is very important, because it means that if you can say, right, if you can write that A mu nu lambda is equal to B mu nu lambda, so if you can write that some tensor that has a certain number of indices, in this case 2 upstairs and 1 downstairs, if you can write down that they're actually equal, then by the transformation laws, which are the same for the left and right hand side, you will conclude that also A prime mu nu lambda is equal to B prime mu nu lambda. So just by coordinate transformations, right, if you have tensors, then they will transform the same way. They will transform the same way. They will have the same factors of dx by dx prime or dx prime by dx, depending on whether the index is upstairs or downstairs, on both sides of the equation. So the equation will be formed invariant. So that is one of the fundamental reasons why, in fact, we want to use tensors, right? Because they have transformation laws that are such that they can preserve equations. So in particular, what we have in this case is that A mu nu lambda minus B mu nu lambda is equal to 0, obviously, right? The difference is 0. And so the statement is that if a certain equation is equal to 0 in one coordinate system, then if it is written in terms of tensors, it will be 0 also in another coordinate system, right? So this will imply that A prime mu nu lambda minus B prime mu nu lambda is also equal to 0, right? And that, of course, it's nothing really fundamentally new as a principle, right? Because it applies to already vectors in three-dimensional space. If a vector, right, is 0 in one coordinate system, when you do a rotation, it's still 0, right? And so here we have the generalization of that to four-dimensional curved space-time. If we write things in terms of tensors, we should really do that, right? Because if we have written an equation in terms of genuine tensors transformed the way we have discussed before, then those equations will be form invariant, right? These equations will be form invariant, will have the same form in any coordinate system, and in particular, if two quantities are 0 and 1, they'll be 0 in all coordinate systems. So that's why we have to develop this kind of formalism a little bit more, right? So we have learned so far that there are certain quantities that are tensors, right? And right, so we have a few tensors, right? And well, we certainly know, for example, the proper time is kind of a trivial tensor because it's a scalar. We know that there are scalar fields. Vectors which are contravariant. We know the coordinate, for example, is one of those things. Let me mention another case, which is dx mu by d tau. This is also a contravariant vector, right? And this would be the four velocity, what we refer to as the four velocity. And we learned that the metric, right, is a tensor, and there is a few more. right? So we have already a rather limited list of things that we can write down, which we know are tensors of one form or another. And so now we want to learn how we can combine these things, right? And well, if something is a tensor, then a linear combination of these things is also a tensor, right? So we can take T mu nu to be some coefficient A times A mu nu, right? Plus some other coefficient B times B mu nu, and that is a tensor also, right? Provided, of course, A and B are tensors. So linear combinations work well, and the reason again is because both of these objects will transform with some appropriate factors of dx by dx prime or dx prime by dx, depending on whether you're looking at the index that is upstairs or downstairs. And so that will apply, of course, to both terms, and so this thing is still a tensor, right? So a linear combination will work. Linear combination will work. A direct product will work too. Take a direct product. So if you know that something is a tensor, for example, A mu nu, if you know that this thing is a tensor, right? And if you know that capital B lambda, right, is also a tensor, in this case a contravariant one, then when you construct the three-index object, which we're going to call again T mu nu lambda, and we have to make sure that we write the indices here in the same location as they appear on that side. So if this index here were upstairs, it has to appear upstairs here, because it does make a difference whether upstairs or downstairs. Then this object is also a tensor, because the first quantity A will transform with some dx by dx prime and dx prime by dx, and the second one will as well, and so the product will do the same thing. So that's fairly obvious, right? And the other thing we can do is a contraction. So not only can we take a product to make a more complicated tensor, but we can also take two objects and sum over one of the indices. So that means that if we have a multi-index object like a T mu rho nu sigma, right, what we can do is we can take these two indices to be the same, so call that rho, and sum over, and that is going to be then equal to a T mu sigma that has just two indices upstairs. So the process of taking two indices and summing them over would give us a tensor of reduced order. And why is it that when you take two indices and you sum over, you don't need to have as a complicated transformation law as you had originally? Well, because of course one dx by dx prime will cancel with another dx prime by dx. Because one was upstairs, the other one was downstairs, and so you have that. So I think these are all neat exercises that you should convince yourself that actually all these things work nicely, and that you can do all these operations. And of course that is going to save us a lot of work later on, because we will be able to construct things that are invariant with relatively little work. And so we can combine all these rules, right? And so for example, we can look at an object which is R nu rho sigma, right, which has three indices, and where we can do the following, where we can take a tensor to start with, which has maybe three indices, S mu, rho, and sigma, and we can multiply that by the metric, right? So in this case by G mu nu, and then sum over mu, right? So here we sum over this index here, right? And so that's a contraction, right? Except that we're not contracting indices within the same tensor, but you're contracting indices with different tensors. But remember, this thing as a whole is of course a tensor, even when the indices were different, because it was a product of tensors. When you have a product of tensors, that's still a tensor, and the contraction does not change the fact that now you still get something that is a tensor, but it has fewer indices, right? So all these wonderful operations are very helpful. And So we can use the metric. The metric is useful in many ways, but also in lowering and raising indices, because you can start out with an object that has two indices upstairs, and now you can multiply by g rho mu, right? And then you can multiply by g sigma rho, right? And these indices are summed over, and so that will just give you a Kronecker delta, right? And so this is equal to T sigma nu, right? T sigma nu. So the metric can be used to lower and raise indices, and if you raise and lower sufficiently many times, then you get back to what you started with, right? So you can, some people I think that have been active in the field of general relativity usually referred to the exercise of teaching a general relativity class as doing a lot of raising and lowering of indices, right? Because there's a lot of that comes in, and you have to be careful, because remember, an index that is upstairs is very different from one that is downstairs, because the transformation properties are quite different, right? And so that in particular means, so there's a thing that I should point out about notation, right? In general, when you have an index upstairs, so you have 2 mu nu lambda sigma dot dot dot, right? If you have n indices, right? If you have n indices for these tensors, then there are 2 to the n possibilities, depending on, you know, having them upstairs or downstairs and so forth. And so it does make a difference if the index is upstairs or downstairs, but we are not going to use a different name. To the n possibilities for index location, right? Because we can have, of course, T mu nu, and then lambda sigma, and dot, 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 right? Right? So they're clearly different objects because they transform in a different way, but we're going to use the same name. Right, we're going to use the same name because we can't really use a different name every time we raise an index or lower an index. So very confusing. So this convention that the differential geometers developed at the beginning of the 20th century was to always use the same name no matter where the indices were located, because it's essentially the same object, right? It does transform in a different way, but it is essentially the same object. And so it makes sense to just use the same symbol for it, no matter where the indices are located, right? So as a result, we're going to refer to the metric, right? We're going to refer to the metric as g mu nu with indices downstairs or upstairs, even though when it's upstairs, it's really the inverse, right? So we're going to use the same symbol, right? Same symbol when it is upstairs, right? Same symbol. It's still the metric that we're talking about. Now, there are a number of quantities that are not tensors. So quantities that are almost tensors, right? And there's some important examples of that which will be useful, in fact, later on. And so those are called tensor densities. Tensor densities. So they almost transform like a tensor, but there's an extra piece. But the extra piece is sufficiently simple that they're very close to tensors. And so the first one has to do with the determinant of the metric. That is, if you take the determinant of the metric, right? After all, the metric is a 4x4 matrix, right? It can be viewed as a 4x4 matrix, which depends on x, right? And let me put the x dependence here so that we remember, right, that there is always an x here. And so we can calculate the determinant of this thing, and then it's conventional, and I think it's a good reason to do that, to define actually little g to be minus the determinant. because this turns out to be a positive quantity most of the time, right? Remember that the G mu nu has a signature to it, right? It starts out in flat space as -1 and then plus, plus, plus 1, right? So that's the reason for this -1, and we're going to take the square root of this in a little bit. And so this determinant is actually not a scalar, right? And so in order to see what's going on, let's write down G prime mu nu. Right now, G prime mu nu, remember this is a covariant tensor, so there's two factors of dx by dx prime. And we're going to write that in a matrix form. So we're going to write that as dx rho by dx prime mu. And then the original matrix, which is, I said rho, so this I'm going to have this as a rho. And then G rho sigma. And then the second matrix, which is again dx sigma by d prime mu. Dx sigma by dx prime mu, right, in this form. So we write it as a matrix multiplication, right, because you have this index here, and then it's multiplied with this, and this index is multiplied with that, right? So we have, and now we take the determinant of this, right? And when we take the determinant, then we have that G prime, the determinant. Now remember that for determinants, you have the determinant of AB is equal to the determinant of A times determinant of B, right? And so you get the product of these determinants. And of course, one of the determinant is the determinant of metric. The other two are the same, right? So you get the dx, the determinant of dx by dx prime, right? And you're going to get that twice, right? The Jacobian matrix, right? Jacobian matrix, the matrix built out of the derivatives of the x with respect to the x prime, and then times the determinant of this guy. So that is just G, right? Or minus G. The sign cancels out, so it doesn't matter. Right? So what this shows us, of course, immediately is that the determinant of G is not a scalar, right? Because if it was a scalar, then there wouldn't be this factor in here, right? It would be just 1, right? A scalar is that phi prime is equal to phi, right? Does not change at all, and the coordinate changes. So here, it changes by some number, right, which depends on x, right? And so that means that the metric, the determinant of the metric is a scalar density. It's called a density because it does change by some power of this dx by dx prime. Right, we'll see that this is relevant because in a moment we'll come to the volume element in four-dimensional space-time. So we need to sort this out. And so in general, we define a tensor density of weight W, tensor density of weight W, an object that transforms like a tensor up to a factor of dx by dx prime to some power. So tensor density, script T prime mu nu, right? So the primed one transforms like, well, it has an index upstairs and one downstairs, so it will transform like dx prime mu times dx lambda downstairs times dx sigma times dx prime nu, right? And then times the same density, tau lambda sigma lambda, right? That would be if it was just a tensor, right? But here you have an extra factor, and the extra factor is dx prime by dx to some power w. Some power w, right? So in our case, because of the power 2 here, and the fact that we have defined a tensor density to have a factor which is dx prime by dx and not dx by dx prime as we have it here, then we have that for the determinant of the metric, W is equal to -2. So the determinant of the metric is a tensor density of weight equal to -2, right? And now, the reason why this is useful, right? The reason why this is useful is that when we consider the volume element, the volume element in four-dimensional space-time, right? And the volume element in four-dimensional space-time, well, that to start with is just d4x, right? But when you do a coordinate change where x, mu, goes into x prime mu, then this volume element changes, right? So d4 x prime is not equal to d4x, but it is equal to dx prime by dx, this Jacobian matrix, right, times dx. Right. And so that is a result of multivariate calculus, right? In multivariable calculus, you remember that when you do a change of variables in whatever dimension you're in, you're going to pick up this Jacobian matrix. The determinant of the Jacobian matrix comes in. And so the relevance of this is that that thing is not invariant. This thing is not invariant either. But the product of the square root of g times d4x is an invariant. Right? So the exercise was useful because it allows us to determine that even though the determinant of the metric is not a scalar and the d4x is not a scalar either, if you take an appropriate product of the determinant of the metric times d4x, then that is invariant. So we would call this, if you want, you can call this as the volume element, right? The volume element in four-dimensional space-time has to have that determinant of the metric. Now, of course, if you are in flat space, that's irrelevant, because in flat space, the metric is just 8 alpha beta. It's just a number, right? And so there's a factor of 1. So in flat space, there is a 1. So, but in curved space, that determinant plays a role, and you can't leave it out. It has to be there. And so, all right, so we learned something new. And now we are going to, I'm going to mention one more tensor that plays a role, which has a very simple form. Remember, we talked about Kronecker delta. Right? The tensor list so far is that we have things like g mu nu, and we have now the g mu nu with the index upstairs, and we had also this Kronecker delta mu nu and a few other things, including that thing which is a scalar, right? And we often encounter also this object, which is epsilon mu nu lambda sigma, right? Which is so-called Levi-Civita density. Levi-Civita density, which has some use in general relativity, just like the epsilon ijk has a use when we discuss electromagnetism, right? So if you're in three-dimensional space, then that's all you can have is an epsilon ijk. But when you transition to four-dimensional space-time, then you have four indices for this completely antisymmetric tensor. And in fact, this thing is not a tensor, and I'll leave that as an exercise to in fact show that you need 1 over square root of g. In other words, the Levi-Civita density, the symbol here, right? Remember that it has the property that epsilon naught 1, 2, 3 is equal to 1, and then it changes sign whenever you interchange a pair of indices, right? So it is completely antisymmetric in all the four indices that we have in this case. That object itself is not a tensor, but it can be fixed up quickly by dividing by the square root of g. And then it is, in fact, a tensor. All right, so we've gathered an assortment of different objects that can be used in constructing equations that are generally covariant. Unfortunately, most of the stuff we have done so far did not involve derivatives, right? And we know that derivatives play an important role, say in Maxwell's equations, lots of derivatives in the field equations. So we're still a little bit away from being able to write anything that could be a plausible candidate as a field equation for gravity, because we don't have derivatives yet. And certainly one of the objects that we have encountered so far, which involves derivative of the metric, is the affine connection, right? Affine connection, right? It enters into the equation of free fall, right? And so it's a gamma lambda mu nu of x, right, which is defined as suitable combination of derivatives of the metric. Now, we originally defined the affine connection as gamma lambda mu nu. Remember, it was defined in terms of a coordinate change from a freely falling coordinate system, which was the xi, to an arbitrary coordinate system. So it was defined as defined originally, right? Put that in parentheses, as dx lambda by dxi alpha, right? And then times the second derivative of xi alpha with respect to dx mu and dx nu, right? That is how it was defined. And then you can rewrite it also in terms of the metric. But the point is that here, you can do a coordinate change. Next, do a coordinate change where x mu goes into x prime mu. And now you can calculate gamma prime lambda mu nu. Right? Well, that's a little bit of an exercise in manipulating indices. First of all, this quantity with the prime is equal to exactly that where everything has been primed. So this is, of course, equal to the x prime lambda by dxi alpha times the second derivative of xi alpha with respect to x prime mu and x prime nu, right? That's obvious, right? Everything has been primed. Now you can write every derivative where you take the derivative by dx, you can write this as the derivative with respect by x prime of dx prime by dx, right? With suitable indices everywhere, right? So every derivative can be written in this way, and so that applies to this here as well, where in fact you're going to do the opposite process, right? Where d by dx prime is going to be written as something with respect to x with dx by dx prime. Right, so you can apply this, you can apply that to here, and to here. Right? And again, we don't want to do this in detail, right? So let me just state the result. Right? It is all pretty straightforward. I mean, we've done a few of these already, so I think after a while they just repeat themselves, and you just go blind looking at all the indices that you have to keep track of, right? And so the result is that gamma prime lambda mu nu is equal to dx prime lambda by dx rho, and then dx tau by dx prime mu, and dx sigma by dx prime nu, right, times gamma with the indices that are not summed over, which are the rho, the tau, and the sigma. So rho, tau, and sigma, right? Well, if this was the whole answer, then we would conclude that gamma is indeed a third-rank mixed tensor, right? Which would mean that if it is 0 in one coordinate system, then it will be 0 in all coordinate system, and that it is a genuine tensor. But unfortunately, that is not the case, because there's an extra piece. So when you do this substitution, you get an extra piece, which is dx prime lambda by dx rho times the second derivative of x rho with respect to x prime nu and x prime mu. Dx prime mu. Mu and nu, and rho. Rho and lambda summed over. Okay. So the presence of this term, which is not proportional to gamma, this inhomogeneous term, implies that gamma lambda mu nu is not a tensor. It's not a tensor. So there are things that look like tensors, right? They have all the indices, right? Upstairs and downstairs, and we call them mu and nu, and they're not tensors, right? So the fact that you have indices doesn't mean that the quantity is a genuine tensor, right? So the affine connection is the first example of something that would have been a prime candidate, but in fact it is not, right? And that, of course, raises a question. Because if indeed the affine connection is not a tensor, which means that it can be 0 in one coordinate system, but it will not be 0 in another one, right? That there is this coordinate dependence. If that is indeed the case, that raises one fundamental question, right? There's something we need to worry about at this stage. Going back to the lecture from last week, right? Equation of free fall, very good, right? So you have the equation for free fall, which is the second derivative of x mu with respect to tau squared plus gamma mu lambda sigma times dx lambda dx sigma, right, by d tau, and by d tau, that is equal to 0, right? This is the equation of free fall, right? And so what is the worry? The worry is that because gamma is not a tensor, right, that puts this equation in jeopardy. Why does it do that? Because this object here is not a tensor, so the concern is that the whole equation will not look the same in different coordinate system, right? That this equation will be valid in one coordinate system, and in another coordinate system, it will be this equation plus some extra piece, right, where everything is primed. So in another coordinate system, you'll have dx prime, you'll have a gamma prime, you have dx prime, but then there's going to be an extra piece, right? And so that would make it a rather undesirable type of equation because it would just not be invariant. And the answer is no. No, this equation is in fact form invariant. This equation is form invariant. And so how does that happen? Well, all right, the gamma is not a tensor because of the inhomogeneous term, right? So when it transforms, when you do the coordinate transformation from x to x prime, it picks up an extra piece, which is the one I just wrote. What about this guy here, dx lambda by dt? Well, we do know that the coordinate with the index upstairs is a genuine contravariant vector, right? And we also know that when you take the derivative with respect to a genuine scalar, which is the proper time, you still should get a genuine contravariant vector. We also know that when you take the product of these two things, you are taking the direct product of two vectors, which should give you a genuine tensor because we stated that products are okay. We also stated that when you take one index and another index and you sum it over, which is doing a contraction, that also is okay, right? So where is the problem? Well, the problem is that when you take one derivative of a 4-vector, you do get a 4-vector, but when you take a second derivative, you don't, as we'll see. Okay, so in fact, this thing is not a 4-vector. And guess what? the piece that you pick up when you do a coordinate transformation of this guy cancels exactly that one. And so the equation is invariant. Okay? So the equation of free fall is in fact invariant in spite of the fact that the gamma itself is not a genuine tensor because there is a cancellation between the first and the second term, right? And so this equation is okay. Now, that should come not entirely as a surprise, right? It does not come entirely as a surprise because in fact we do know, we do know quite well that this equation is not form invariant. Why is it that we know that that equation is not form invariant from the very first lecture we had? Because we do know that there is a special coordinate system, which is denoted by psi, where we do know that the second derivative of psi alpha with respect to tau squared is in fact equal to just 0, right? So we do know that there is a special coordinate system where gamma alpha beta gamma is in fact equal to 0, and that is a freely falling coordinate system, right? So this result does not come as a surprise. Does not come as a surprise because if we had followed carefully what we've done so far, we do know that in fact in a freely falling coordinate system gamma is 0. Gamma is 0, right? And we do know that in an arbitrary coordinate system it is not 0. So the fact that it is not a tensor does not come as a surprise at all, right? But it is encouraging that in fact this equation that we had and that we cherished, right, for a few lectures, that equation in fact survives because there's a little cancellation, right? So that means, right, that Einstein in 1911 is trying to write down a field equation for the gravitational field, and he figures out that the metric is an important thing, and then he says, well, I have to have derivatives, right, because that's what appears in Maxwell's equation, for example, right, or Poisson's equation, right? Have to have derivative of the field, so a good candidate to write the field equation is the gamma. And no, the gamma is not going to work because the gamma is not a tensor. Right? So you have to find out something that you can do with the gamma that it will eventually give you a tensor, right? The gamma itself won't work by itself, right? It's not the F mu nu of gravitation, right? It's not the E and B field of gravitation because it's not a tensor, right? So you have to do some further work, and what you find after a while is that in fact you take one more derivatives of these gammas and you get the Riemann tensor, and that is a tensor. That is a tensor. That will work. So finally, you have the object you want. Well, we just have a few minutes left, but I think this is a good place to stop. Occasionally, we've run a little bit over. So for once, I think we'll end maybe 1 or 2 minutes early, right? And so if there are any questions.
Was the geometry of this developed by Riemann at the time that
Absolutely.
Einstein could refer back to?
Absolutely. So differential geometry was first introduced by Gauss, as I mentioned in the first lectures. Gauss just dealt with surfaces, right, which was the easiest thing. And then, hold on. And so then it was Riemann that generalized that to higher dimensional geometries, right? So he introduced the concept of non-Euclidean geometry in 3 and 4 dimensions. And it was Riemann and Christoffel, two German mathematicians, that understood that there was this connection which played an important role, right? And they realized that the connection had, in whatever notation they were using back then, which is probably horrible by today's standards, by what we're used to. Of course, to them it was easy to use, but to us it would be very difficult to read their papers because they did not use lowering and raising indices. And they realized that it was not this gamma that would do the trick, that if you wanted to describe invariant properties of a surface, that is physical, real physical properties, have nothing to do with how you draw coordinate systems, that you'd have to involve the curvature, right? Because at every point on the surface of the Earth there is a well-defined curvature, and that curvature has nothing to do whether I use y coordinate system, which has x going this way and y going that way, or your coordinate system, which has x going this way and y going this way. The curvature is well defined, right? The so-called principal radii of curvature and so forth. So Riemann and Christoffel figured out that you had to have a tensor, which was this Riemann tensor, and that would describe the curvature in the correct way. And that was, last decades of the 19th century, 1880s, 1870s, and so forth. And then after they introduced this Riemann tensor, then people found out all sorts of identities named by, like Bianchi identity, Ricci tensor, and so forth. That development was 1901, 1902. Very recent, very recent. So at the time, Einstein was speculating on what his theory might look like. This mathematician had just written down, the most important and useful results. And so Wikipedia at that time was not available, right? And there was no internet, right? So all the communications were done by pieces of paper and stuff, which took forever, for libraries to print first the papers to get published and then get printed and distributed to libraries and so forth. And these were mathematics papers, so Einstein did not learn about them until Marcel Grossmann told him there is this thing called differential geometry. We gotta read about it because it could be relevant. And so in 1911, 1912, they started to read these papers and try to sort out. And still, until the very end, until he was just in the final stages of writing down his 1916 papers, he was not aware of some of the identities that would actually be relevant for his field equations, notably the Bianchi identity. So there were some issues in trying to exactly understand what the correct field equations were supposed to be based on these complicated differential identities that the Riemann tensor obeys. The Riemann tensor is more complicated than anything else we have in electromagnetism because it has 4 indices, right? So those 4 indices can be raised and lowered, and you can do contractions and so forth. And so it's a messy object to work with, and try to understand exactly which indices should be used in the field equation is not trivial. It's not trivial, yeah. Any other questions? All right, so I'll see you next week then.